Greetings, wonderful Physics 111 students, and welcome back to Physics with Captain Rod. I'm making this one here to help you out with your Unit 4 on third homework here. We're going to discuss numbers 1, 2, and 3. And the first thing I'd like to talk about here before we talk about 1, 2, and 3 are just kind of units. So you'll see in the study of thermodynamics, you'll see a term called a calorie. And a calorie is just a thermodynamic energy unit. It's equal to 4.186 joules. And you'll also hear a term called a food calorie. This is the terminology used, on the side of food containers. And what that is it's a kilocalorie. So a food calorie is equal to 4,186 joules. So when you see a candy bar and it says 30 calories, by the way, it's 30 kilocalories. That means 30 of these things. But anyway, getting on with your homework here. So we're going to chat about number 1, and I've kind of cut and pasted it, but I see I missed a little bit of it. It says to convert 4.05 times 10 to the third calories to kilocalories. So the first problem is just a conversion to kilocalories and to joules, and you're using these conversions right here. So I'm going to consider that done. Okay, number 2, let's see. It says Lake Erie has about this many cubic meters of water and a whole bunch of walleye too. Let's see. Assume the water's density is that of water at 20 C in 1 atmosphere. Now I'm going to let you look that up. You're going to look up the density of water. And remember what density is. It's mass over volume. Or equation-wise, I might have wrote it like this before. Density equals mass over volume. Whether you call it D for density or this is the Greek letter rho to represent density, doesn't matter. Look up the density. They gave you a volume. Then you're going to calculate a mass. Now, when it says how much energy is required to raise its temperature, right, that's a specific heat type of problem, right? And remember the formula for specific heat. Q, your heat, is equal to mc delta T, right? And again, where this Q is your energy or your heat, typically in joules. If your specific heat is a number with units of joules per kilogram degree centigrade, you're going to want to look that up for fresh water, your mass you're getting from over here, and the delta T is given in the problem. And that should be enough to get you through part A. Let's see, how many years, or in other words, how long would it take a 1,400 megawatt generator to do this, basically? So that megawatt is a unit of power, which remember is change in energy over change in time. Okay. And what you're going to do is you're going to take your answer for A, how much energy, and use that here for this. And then this is your power, which is going to go here, and then you're going to solve for delta T. Mega, remember, means 10 to the 6, so that's 1,400 times 10 to the 6 watts. And that should get you to your delta T, which, by the way, will come out in seconds, and then you'll convert to years. All right, let's get that third one discussed. Let's see. And I need some room here. Just going to get rid of all of this if you folks don't mind. Okay, it says, let's see, a copper block with a given mass slides over a surface. So, right, we've got a certain block of copper. I'm going to call this position 1, and this thing's moving. And eventually it stops. I'm going to call this position 2. And what I'm trying to do here is I'm kind of model this like a work energy problem, because I think that's basically what this is. And you're given a speed here, so you're given a V1. Now, it doesn't say how far it slid, but if we did a free body of this object, it would look something like this. You got a gravitational force. Remember our surface in contact, that's going to give you a vertical or an upward normal force. And then a frictional force is what's going to stop that. And this thing right here causes a heat transfer. Basically, the surfaces get warm here and here along the table. All right, so what you want to do is write out the work energy theorem, and I'm going to kind of speed this along. You're going to have a KE1. You're going to have whether you put plus work or minus work, believe it or not, it doesn't really matter. I'm going to put minus work due to the friction equals your KE2 is basically 0. Now, this now is a positive number when you solve it. Now, the big question is that work. What happened to that energy. You'll notice that the kinetic energy went from some value to 0. Well, what happened is it got changed to molecular kinetic energy in the warming of the bottom of this object and the warming of the tabletop surface. So in the problem, what they're saying is to assume 85% of the kinetic energy is absorbed by the block. So what they're going to say is that the heat, we're going to say, that goes into the block is going to be 0.85 times this, the work done, or we could say times this, the initial kinetic energy, whichever you kind of prefer. It doesn't really matter, because you can see from this equation they're equal. Once you do so, then we're going to use the specific heat equation, Q equals mc delta T, to calculate a temperature change. Okay, and you're going to probably get a very small value. So that should be enough to get you moving on that. I hope that gets you moving. Have a great day.